Good morning, good afternoon. I think that it is the time to start with only 5 minutes of delay. My name is Kyriazis Pitilakis from Aristotle University. And it is the next keynote lecture, which will be given by Rathje. It is really my pleasure to introduce her. She is a professor in the University of Texas with a lot of work done in the geotechnical earthquake engineering, and in particular in site response, seismic slope stability, earthquake-induced ground failure, and remote sensing. He has been funded by many good funds in the United States. And now she is very well known because she is the person of the design-safe cyberstructure. Everybody knows, everybody would like to use it. If you want more details, you can go to Ellen, and she is the right, really the right person on that, which is very, very important infrastructure. She is also a co-chair of the well-known GEAR Association, which makes very good reports after strong earthquakes. From the professional and consulting point of view, she has extended her experience with the consulting in major projects in the nuclear power energy all over the world and in the United States. She has been a member of the boards of directors of the International Association of Earthquake Engineering, and not only. And she got a lot of honors and awards. I would just mention the PEC one, if I remember well, yes, the PEC award, which has been given in 22, and the Joiner one, which has been given in 2010. So it is the right person to speak. She's going to develop a very interesting talk regarding the slope displacements, the design of slopes, but in the light of extended infrastructures. I believe that it is very interesting. The floor is yours, Ellen. Thank you very much. It's really my pleasure.
Well, first of all, thank you, Kyriazis, for that wonderful introduction. And I want to thank the organizing committee for this great opportunity to talk to you today about some of the work we've been doing on regional scale seismic landslide assessments, in particular for distributed infrastructure. Now, if you look at this title, you might ask 3 questions. First, why landslides? And if you look at the impacts of earthquake ground shaking, one of the secondary impacts is often landslides. And here are just a list of a couple, just a few earthquakes where there were significant landslides induced by ground shaking. And sometimes those landslides cause, drag all the soil down the slope down into a city. Sometimes you see a rotational failure. And sometimes you might just see some moderate deformation, but all of these types of movements can cause damage to the surrounding infrastructure. The second question you might ask is why regional scale? And I like to use the Kaikoura, New Zealand earthquake as an example. So here on the right, you can see a map of the northern part of the southern island of New Zealand where the Kaikoura earthquake happened. And every dot on this map represents a landslide that was documented and observed from that earthquake. And while as engineers, we might be able to evaluate or predict any one of those individual landslides, to really understand the impact of these landslides on the area, you really need to understand how many of them there were and their regional distribution. So you can really only see that at a regional scale. And if we look at the impacts, particularly for this earthquake, there were a significant number of landslides that took out both the coastal highway as well as the train infrastructure, which completely devastated the movement of goods across the South Island of New Zealand for many, many months. Additionally, there were landslide dams where the landslide debris came downslope, blocked a river, and then you get basically an unengineered dam holding back a reservoir. And there were significant concerns of the impacts if there was an uncontrolled release of that water. So again, to understand the impact of this earthquake, and in particular the landslides, it was understanding the pervasive distribution of landslides that was important. The last question you might ask is why distributed infrastructure, and that relates to the last thing I just mentioned. Now, distributed infrastructure, as the name implies, extend over a wide-ranging area. So if you want to look at the impacts of an earthquake, and in particular the earthquake-induced landslides on the distributed infrastructure, you need to understand the regional distribution of those landslides. And in particular, when we look at things like gas pipelines or any type of pipeline network, often the main component or the main driver of damage is the ground deformation. So that ground deformation from a landslide bringing the pipeline along is what causes the damage. So with that as an introduction, let me take you through an outline of the points that I'm going to make today. So first, we're going to zoom in to a single slope, individual slopes, and look at the seismic performance of earth slopes and some of the methods that we use and some of the new methods that we're developing for this case. Then we'll zoom out and look at regional scale assessments. So how do we take those methods and apply them at a regional scale? How do we deal with uncertainties? And in this context, I'm going to be talking about applying this methodology to the entire state of California, which we were tasked to do for a project that was funded by the California Energy Commission. And then finally, we'll zoom back in and look at how we can evaluate the impacts on distributed infrastructure. In particular, how do we identify landslide zones? And then importantly, how do we quantify the parameters that influence the damage to the pipeline? So how big are the landslides? How much are they moving? And in which direction do we expect them to move? Okay, so let's get started. So when we look at the seismic performance of earth slopes, we've very much moved into trying to predict the deformations of a slope and potential failure during earthquake shaking. And in fact, the parameter, the response parameter that we commonly use is the displacement. And I'm going to call that capital D. So that's the seismic movement, typically downslope, almost always, for the failure mass or the slope under consideration. Now we can look at the evolution of the methods that we use to predict sliding displacements. We started more than 50 years ago dealing with a rigid sliding block approach. So in a rigid sliding block approach, we drill down into the slope, we characterize the properties, we do our limit equilibrium analysis, which we're really good at doing, and if it was a static problem, we would just compute the factor of safety. But because we're going to want to look at the seismic response, instead, we compute something called a yield acceleration, or KY. And KY, when multiplied by the weight of the sliding mass, essentially represents the downslope destabilizing force that results in a factor of safety of 1. So obviously, if the acceleration is greater than KY, factor of safety is less than 1, and we should expect some movements. Now, after having done this detailed evaluation and limit equilibrium analysis, we're going to take that detailed model and then idealize it as a rigid sliding block moving down an inclined plane where the only thing we pull from the first analysis is KY. And then we look at some time series. And as I mentioned earlier, if we look at acceleration versus time, and here's the yield acceleration, let's say it's 0.1 g. Anytime the ground motion exceeds 0.1 g, the factor of safety is less than 1, and we expect accumulating downslope movement. And obviously, every time we exceed the yield acceleration, we get additional movement that accumulates, and then over time, by the end of the earthquake, we've got some downslope movement that we can quantify. Now, just like any engineering analysis, there's a range of assumptions that go into it. So the two key assumptions in this analysis is that the movement that we compute is localized on a well-defined slip surface. For the sliding block, clearly here, but maybe on the sliding mass, the equivalent is along the slip surface. And then the second assumption is that movement occurs only when the strength is exceeded. So essentially, we're modeling the slope as rigid, perfectly plastic. So no deformation before failure. Now, as I said, this approach was developed many, many years ago, and it was quickly clear that we needed more than just a rigid sliding block. We believe in dynamics, and people realize that there is a finite flexibility to the slope system that we have to take into account. So we want to look at the dynamic responses of the slope as well as the sliding response. And so when we look at a flexible sliding block, we still start with our slope with a ky and a yield acceleration, but we want to characterize the dynamic response, and we do that through some type of fundamental period. And in this case, you might say we've got our critical failure surface. We can come up with some representative thickness of the sliding mass. We have the shear wave velocity of the material, and so maybe we can just say, if we take 4 times the height over the v sub s, that represents the period of the sliding mass. Now, with these parameters, of course, then we need to characterize ground shaking. And as we all know, ground shaking, we have to always worry about not only intensity, but frequency, content, and duration. And of course, even for a rigid sliding block, these parameters are important, but for a flexible sliding block, perhaps even more important because you have that dynamic response to consider as well. Now, any engineer can do this analysis and then go, select a bunch of time histories and run your displacement analysis. But generally, we've developed response models that help you do that. And in fact, these days, you might call these surrogate models, now in the AI machine learning language, where we run a bunch of these flexible sliding block analyses and then develop some sort of statistical relationship that predicts displacement as a function of slope parameters, ky and ts or others, and ground shaking parameters. And there's a whole suite of them out there. I just listed a few, including some that I developed here. Now, of course, in practice, many of you have moved on and are running stress deformation analysis. So we can run finite element, we can run finite difference analyses, we can model the full geometry of the slope, impart an acceleration time history to the slope, and then calculate the displacement of the slope at any location as a function of time, and then now we have another estimate of displacement. But the key when we evolve to this type of analysis is a lot of the assumptions we made no longer need apply. So we no longer assume a slip surface. Wherever the movements want to accumulate, they accumulate. The deformation does not need to be localized. We can model the nonlinear stress-strain behavior. So it's no longer rigid, perfectly plastic. We've got nonlinearity. And because of that, we can accumulate permanent deformation, permanent movements before failure. So they're going to accumulate along the way. So in this first part of my talk, I'm going to discuss how we've developed surrogate models to predict displacement from a large suite of finite element simulations. So let's first talk about the finite element models that we developed, and this work was all recently published in the ASCE Geotechnical Journal. So when you do surrogate models on sliding block, you can just say, ky is this, ts is that, and you're good to go. But now, when you do this, when you develop finite element models, you have to develop true slopes that you're going to analyze that run the gamut of all the other parameters. So in the way we did that, we came up with this generalized model where we have a thickness of soil, which is represented by the height of the slope plus some distance below the toe of the slope, then a stiffer, stronger material below that, and then bedrock. And we varied the height of the slope, that depth below the toe of the slope angle, beta, the strength parameters, of course, both C-phi combinations and phi equal to 0. We varied the shear wave velocity. And within all of those, we had a hyperbolic stress-strain response such that at large strains, we were modeling the strength appropriately, but even at small to moderate shear strains, we were modeling stiffness that was consistent with what we know from modulus reduction and damping curves. And all of these analyses were run with LS-DYNA. The important thing that I've also shown here is that for every finite element model, even though we didn't need to do a limit equilibrium model, we did a corresponding limit equilibrium analysis because our surrogate model is going to want ky as an input. So we wanted to know what ky's are associated with our slope models. And the other thing that came out of that limit equilibrium analysis was the critical slip surface. Okay, so as I'm sure many of you are aware, the depth of the critical slip surface tends to be a function of the relative values of cohesion and friction angle. And so when you have friction-dominated, low cohesion, you're going to get shallow slip surfaces, and as you get more cohesion-dominated, you're going to get deep slip surfaces. So this is something we wanted to investigate, how the thickness and the depth of the slip surface impacted the results. So we developed 49 different slope models, and of course we had a range of ky. So every point on these two graphs represents a different slope model. So you can see ky ranges from about 0.025 G to about 0.5 G, so a good range there. Now, previously I mentioned that the period of the sliding mass had been an important parameter. And as we evolved and looked at our data, it turned out that the period of the sliding mass didn't appear to be as important as the period of the slope, which we defined simply based on the height of the slope and the shear wave velocity. So that was what mattered. It wasn't necessarily the height of the slip surface. So, and I'll come back to that concept in a second. But basically, the period of the slopes for the slopes we analyzed went from about 0.3 to 0.6. We did want to characterize the depth of the sliding surface, and we did that through this parameter H ratio, which essentially represents the ratio of the thickness of the sliding mass to the height of the slope. So if this ratio is small, so here's H ratio versus ky, 0.1, 0.2, the thickness is only 20% of the height. So those are shallow slip surfaces. And as the slip surface goes deeper, H ratio, in our cases, got as large as 2. Of course, we had to run a bunch of motions through these finite element models. So we ran about over 1,000 motions through each finite element model. We got these ground motions from Christy Hale, who did her PhD at UC Berkeley with Norm Abrahamson and Jonathan Bray. And these are some processed NGA West 2 ground motions. You can see they range from magnitude 5 to almost 8, many different distances. VS30 greater than 300 meters per second. Now, of course, we were interested in seeing which intensity measure best predicted displacement. So we did not only look at peak ground acceleration, but we also looked at peak ground velocity, Arius intensity, CAV. I'm a big believer in frequency content, so mean period we also looked at. And one way you can look at least the distribution of these parameters for your data set is to simply plot one parameter versus the other parameter for each individual motion. So each point on this plot represents a ground motion. So you can see PGA went from about 0.01 G to 1 G. Peak ground velocity also changed by orders of magnitude, Arius intensity and CAV as well. Clearly, there's a lot of correlation between PGA and PGV, and PGA and Arius intensity and CAV, and not surprisingly so. TM, however, does give you a completely orthogonal piece of information about frequency content. You see there's basically no correlation. So that's also potentially useful. The last thing to mention here is that we wanted to make sure we had enough motions in this upper corner, which is where the design motions may end up being, above 1 G, above 100 centimeter per second PGV. So we did take 153 motions and scaled them from kind of this black cloud up to the red cloud in the corner. Okay, so with 49 slope models, 1,000 ground motions, you can do the math. We ran a lot of analyses. But before we look at analyzing or trying to regress among those analyses, it's always good to look at the results and see if they make sense. So what I've shown here are some displacement contours. So these are displacement after the end of shaking. At the top, to shallow slip surfaces, which are from friction-dominated materials, and down here to deep slip surfaces. And what you see are the black lines, the black circles, represent the critical slip surface from the pseudostatic analysis. In color are the displacement contours, the displacement amplitudes, where red are the largest displacements. So the first thing I hope you notice is that most of the largest displacements are encapsulated within the critical slip surface. So when we predict shallow slip surfaces, the largest displacements tend to be near the slope. When we predict deep slip surfaces, the largest displacements are encapsulated within that slip surface. So that is good, makes sense. Now, if you look at the deep models, the other thing you see here is on the left is a small ky, and on the right is a large ky. And if you look at the maximum displacements, we've got 35 centimeters versus about 8 centimeters. So again, this makes physical sense. As ky increases, and this is all for the same ground motion, we get less displacement. Now let's come up to the top two here, because these were the surprising results. So if you look at the displacements on the left for the low ky, or small ky, about 9 centimeters, but for the large ky, about almost 5 times as large, the displacements are just a tiny bit smaller, which is, in fact, somewhat shocking at first. Ky doesn't matter. Talk about blowing your mind if you're a seismic slope stability person. But if you start looking at the displacement distribution, it starts making sense, because look at how much distributed shearing happens below the critical slip surface. So we're getting shear that's not only represented or occurring due to shearing on the slip surface, but you've got this distributed shearing. And you basically have that slope that is shaking and moving downhill due to these strains. Now, again, it still may not be clear why this is happening, but we do have another paper we just recently published in Soil Dynamics and Earthquake Engineering that goes into a little bit of the mechanics of why this is happening, where at shallow depths, with these friction-dominated materials, the shallow slip surface is critical because that is where the static shear stress is closest to the frictional strength, and the frictional strength is low near the surface because the overburden pressure is small. At depth, the ky is bigger because the strength gets bigger with depth, and there's a bigger difference between the static shear stresses and the strength. So that makes sense. But what happens during an earthquake is that the dynamic shear stresses at depth are larger than they are near the surface. And it's those larger dynamic shear stresses at depth that generate movements well below that critical slip surface. And it's something we have not modeled that I'm aware of in any of the sliding block type analyses. Okay, with having some confidence in our displacements, we went towards identifying the best intensity measures for looking at displacement. So the way we did this is we first looked at an individual slope and plotted the displacement data across all 1,000 motions as a function of the different intensity measures. And fortunately, we see displacement going up as ground shaking goes up. So that, again, makes sense. Noticing these are on a log-log scale, we can just simply fit a log-log, a straight line through the log of these values, and that's what's shown in the red. And then what I want to really point out is the scatter in the data, right? The unexplained scatter around that red line. And it's clear that PGV is got the least scatter. And you can quantify that using the standard deviation in natural log units. And those are listed here. You can see 0.8 for PGA, almost half of that for PGV. Areas intensity is somewhat in the middle, and CAV is even higher than PGA. So this, it seems to indicate that PGV is a big player here. Now, I've done some work in looking at vector hazards, so trying to understand if a second ground motion can help. So we did something similar where we did different combinations of two ground motion parameters to see where things fell out. I'm not going to plot some 3D plot that you can try and look at the scatter in 3D, but we did compute sigmas, so we'll look at the sigmas for these single intensity measure models and two intensity measure models. So again, first looking at the single intensity measure models, you can see PGV is winning by a lot. Even once you add magnitude to PGA, which you might say, well, I needed that for duration and frequency content effects, PGV still wins out. What was surprising, though, was when we went and looked at two intensity measure models, PGA, PGV, Arius intensity CAV, Arius intensity and mean period. What you find is almost no pair can do better than PGV alone. You might argue Arius intensity and mean period can get you a little bit there, but these dots all represent different slope models. So there's like some slopes it helps and some slopes it doesn't help, where for PGV, things are pretty tight. So based on this assessment, we recommend using peak ground velocity as the sole intensity measure. Because once you go to vector, you've got to deal with correlation, stuff you just don't want to deal with. If you can get it done with one intensity measure, I recommend you always go in that direction. And in fact, this makes sense why PGV wins out. And the way I like to think about it is with PGV, you get two for the price of one. You get intensity and frequency content in a single ground motion parameter. Now you might be like, how does that work? We have to think about how PGV is computed. You have an acceleration time history, you integrate it to get the velocity time history, and you get the peak from the velocity time history. If you have a high frequency acceleration time history, you don't have a lot of area, you don't get a large PGV. So PGV is affected by both the intensity and frequency content of the acceleration time history. If you take only one thing away from this talk, it's that you should check out PGV as a ground motion intensity measure. In fact, with my graduate students, the joke is PGV is my third child. That's how much I love PGV. Very good, because I was about to say you're allowed to laugh at my jokes, okay? All right, even better. All right, so with all of that data, we developed what I would call a classical regression model. Since we saw that displacement varied linearly with the natural log of PGV, we simply fit a very simple equation here where A0 and A1 are a function of the slope parameters. All the slope parameters are in the paper. I'm not going to go through them here. But what I want to point out is that we had to develop a separate model for shallow slip surfaces, which we defined as a H ratio less than 0.6, and deep slip surfaces, which we defined as a H ratio greater than 0.6. For those shallow slip surfaces, T-slope, we have T-slope NKY, but T-slope matters way more than KY. For the deep slip surface, T-slope didn't matter. It really was just the KY that mattered. And it troubled me, though. I didn't like the fact that we had to discretely define shallow versus deep, because I don't think slopes know I'm a shallow slip surface slope and I'm a deep slip surface slope. It should be more of a continuous distribution, but it was really hard to develop a functional form that would fit that data. Now I'm going to go to the next slide, and you have to see if you can figure out what is different. I'll give you a second. So notice, it's the same model, but in terms of PGA. And I have struggled with this probably for a decade. It's like, give the people what they want. They want a PGA model. They feel comfortable with PGA. So we did it. But even in the paper, we say it's not recommended. And I'll take this a step forward. These are not the droids you're looking for, okay? So forget that I said that, and I will never publish a PGA model again. Okay, so any displacement model doesn't need just a median displacement model. We need the aleatory variability. So we went through the data and quantified that. And something a bit unique is we partition that variability into the between slope variability, tau, and the within slope variability, phi. If you've done ground motions, this is similar to the between earthquake and within earthquake variability. And so the tau that comes from the fact that we ran 49 different slope models was about 0.14, whereas the within slope variability was about 0.4. And we saw that it varied a bit with t-slope and ky. And this is similar to what I showed on that previous slide. So the variability is dominated by the ground motions, not the different slopes. So what do these displacement predictions look like? Here's just displacement as a function of ky for first the deep slip, or for 2 ground motion intensities, a deep slip surface, so that's shown on in black. So obviously as ky increases, displacement goes down by an order of magnitude. Makes sense. If I shake it harder, I get more displacement. But here is, again, the mind-blowing thing that if I show you 3 shallow slip surfaces with H ratio less than 0.6, but 3 different periods of the slope, we can see that displacement does not vary with ky very much, and in fact, it's t-slope that matters, and similarly at high PGV. So again, this is somewhat of a new paradigm. I'm not sure I've seen anyone else observe this. We're continuing to explore it. And what does this mean with respect to how we interpret displacements from finite element simulations compared to what we've been predicting for decades for sliding block? I did want to mention one other thing, because I said that I didn't like that we had to differentiate between deep and shallow slip surfaces. We couldn't figure out any better functional form for the model. So we decided, with all the AI machine learning, let's throw all the data in a neural network. And in this case, we didn't just throw in as inputs ky and t-slope, but we gave the model H ratio and said, let's see what it does. Let's see what it comes up with. And what you'll see here is we've got displacement versus ky for 4 different H ratios, a constant t-slope. And you can see for deep slip surfaces, we see what we saw earlier, but for shallow slip surfaces, we see a much flatter response. So it's predicting similar to what we did with the classical regression, but with a continuous variation. If we put in a high H ratio and see what the t-slope effect, all the curves are the same. So even though we allowed the model to use t-slope for any of the predictions, when H ratio is large, it's not there. But if we put in H ratio of 0.2 with the same periods of the slope, we see it there. So the beauty of the neural network was it could find these trends in the data, which were much harder to model analytically with the classical regression. That's the good part. The bad part is the sigma didn't come down that much. In fact, most of the reduction was in tau, and phi only came down 5%, but since phi dominated the variability, we weren't seeing the manifestation there. But reduction in sigma is not the only reason to go to a more sophisticated model. I think this continuous variation of H ratio is more significant. Okay, so now having zoomed in to these new advancements on developing displacement estimates, let's go and try and do this at the regional scale. So when we do this at the regional scale, we now need the regional distribution of ky, and if we're using a flexible model, we need some sort of period of the slope. So how are we going to do this on the scale of the entire state of California, or even on the scale of a quadrangle? So obviously, we tend to turn to a digital elevation model to come up with the slope geometry. We can calculate the slope angle. When we look at soil strength and, say, shear wave velocity, we typically go to geologic maps. So we're going to assign the same properties to the same geologic unit in the entire area. Similarly, for groundwater table, we will look at, say, well data regionally and apply that. And then finally, we need to also consider the method of limit equilibrium analysis we use to compute ky. Almost exclusively, when we do a regional scale analysis, we have to sacrifice. And the sacrifice we often make is that we do an infinite slope rigid block analysis. This makes it much easier to compute ky simply with the slope angle and some assumptions. But I want to emphasize, moving forward, now that we have these flexible models, there are opportunities to use somewhat simplified limit equilibrium methods, such as proposed by Grant et al., where we could put in circular surfaces as well. So there are some opportunities there. And for the work I'm going to present now, this was done kind of in parallel to the other work I just mentioned. So we decided to stick with the rigid sliding block assumption. So when we compute sliding displacements at a regional scale, we need the regional distribution of ground shaking, we need the regional distribution of KY, and then we need displacement models that are going, all three together go to predict the displacement. But of course, when you're applying things at a regional scale, well, first of all, as geotechnical engineers, we always have uncertainty. But when you go to a regional scale, an entire state, there's going to be even more uncertainties. And we need to explicitly account for them. So if we think about on the KY side of things, the KY is going to be a function of cohesion, friction angle, thickness of the sliding mass, and then the groundwater table depth. So all of those things we want to incorporate their uncertainty. There are also different displacement models out there. I just said, or I said earlier, I'm not the only one who's developed displacement models, of course. And so we need to consider that multiple displacement models are out there that give defensible displacement estimates. So to look at the uncertainties for KY, we're going to define the statistical distribution of the input parameters that go to compute KY. And for the displacement models, we're going to consider alternative models. And while some people stand up here and say, use my model, all the rest of the models are bunk, I suggest and recommend that you always use multiple models to do a displacement calculation. How are we going to do this? We heard a little bit about this in Julian's talk yesterday. We'll use logic trees. So just to give you a little primer on logic trees, what we're trying to do is come up with discrete values that we are going to then run through our analyses. So for instance, perhaps there's one input parameter you're interested in. You have a best estimate, you have a high estimate, you have a low estimate, and you weight them with the best estimate higher than the high and the low. And you can see that this somewhat looks like, a normal distribution, high in the middle, low on the ends. And you can think of it that way. Now, maybe the next thing is we're going to use 3 different predictive models. Now here we're not trying to model a statistical distribution. We may say, hey, I think model A is the most defensible. It uses PGV instead of PGA, so I'm going to give it the highest weight. And the other models, for whatever reasons, they may have features you like, features you don't like, you may weigh them down lower. Now having defined these logic trees, and this is obviously a very simple logic tree, I've got 3 inputs, 3 models, 3 times 3 is 9, so I can do the analysis for 9 combinations of inputs and models. And each of those generates a result. In our case, it would be displacements. Now, all of those results are not equally likely. Clearly, the one that's most likely is with the highest weight for the input and the highest weight for the model B, or excuse me, model A in this case. So for each of those results, the corresponding weight is just simply the product of the weights of the path through the logic tree. And then with these results, you can come up with a weighted average, or you can plot a cumulative distribution function. So we're going to use this for our displacement calculations at a regional scale. So how do we assign strength? As I mentioned earlier, we tend to do that based on geologic units, but you need a consistent framework of geologic units. If you go from quadrangle to quadrangle across California, you'll know that in one quadrangle they may call a geologic unit something, and you cross over, and it's called something else, right? Same thing happens at nation boundaries as well. The geology does not know anything about those boundaries. So we were fortunate that Wills et al. Had developed a statewide geologic map for California that had about 15 geologic units consistently mapped across the whole United States. Again, if you're doing it on a quadrangle level, you can just use something maybe a little more detailed for that quadrangle. So then we needed to assign C and phi to each of those geologic units. Only 10 of the geologic units had slopes steeper than 10 degrees, so those were the only ones we had to worry about. And fortunately, we had access to the database from the California Geological Survey with 13,000 borehole samples with cohesion and friction angle. And so we developed mean and standard deviation estimates for each of those geologic units. Something we noticed was for the same geologic unit in Northern California versus Southern California, the statistics looked different, so we incorporated that as we separated those and developed different sets in Northern and Southern California. So if we look at the cohesion and friction angle across geologic units, fortunately we see the strength goes up with geologic age. That makes sense. We also saw that for cohesion, Northern California tended to be stronger than Southern California. Northern California cohesion was greater than Southern California cohesion, and Southern California friction angle was greater than Northern California friction angle. So one seemed to be high C, low phi, the other low C, high phi. So that's how we modeled things. Now, the KY equation also has other slope properties, the thickness of the sliding mass. We used 5 to 15 meters in Northern California, 1.5 to 4.5 in Southern California because of differences that were indicated to us from engineering geologists in the two regions. The groundwater table, again, we looked at well data, looked at multiple value estimates of that, and then we just assumed the unit weight. So if you throw this now all into the logic tree, we've got 3 branches for friction angle, 3 branches for cohesion, 3 branches for thickness, 3 branches for groundwater table. And so each of these, again, had weights of 0.25, 0.5, and 0.25. We incorporated some negative correlation between C and phi. And then we computed KY for all of those combinations, which if you do the math, represents 81 KY values per grid cell. Now, if we look at a single cell, there's going to be a big range of KY because of these uncertainties. If you can develop better strength properties, these uncertainties would go down. But so here's a cumulative distribution function for KY. Most of it's in the range, but the tails do kind of head to low and larger values. Now, with 81 KY values per cell, start doing the math again of 3 models across the entire state of California. The storage requirements just become crazy. And so without really sacrificing much accuracy, we can resample this cumulative distribution function to a fewer number of values of KY before we do our displacement calculation. So where these green dots represent the 81 original KY, if we resample to 7, shown in the red, and this all comes from an approach outlined by Miller and Rice, these 7 KY values with these weights reproduce the full distribution. So we move forward with only 7 KY. We then go to the displacement model uncertainty, or part of the logic tree. So we've talked a lot about these type of displacement models. These were looking at rigid block models, so we utilized 3. You can see them listed here. We gave the model that used PGV the highest weight, because I'm a big believer in PGV. Okay, so now let's just look at some results again on the cell level for 3 different cells at this point. So here's the cumulative distribution functions for KY for a cell with large KY, medium, and small. So you can see here's lower KY, maybe on average about 0.1 G, all the way up to maybe 0.6 or 0.7 G. Now what we're going to do for each of these cells, we're going to resample that to 7 and compute the cumulative distribution, or we're going to compute the displacements for a certain intensity of shaking. So what's shown here is for these values of PGA and PGV. And so clearly, the low KY has the largest displacements, the largest KY has the least. And just for clarity here, anything less than 0.1 centimeters, we plotted at 0.1 centimeters. So quite a range. This is a log scale down here. But that's, again, because we're incorporating these uncertainties. So the last step here is what traditionally might be done, is let's just look first. We're going to use the whole distribution in a minute, but let's just look at the median displacement for each of these. So you come into the cumulative distribution function at 0.5 and pull off 3 different displacement values. And that's what we're going to compute, a map of median displacement. So here, anything in orange has more than 15 centimeters, yellow 5 to 15, green 1 to 5, and less than 1 in gray. Okay, so this is where typically we would stop in a seismic slope stability or a seismic landslide hazard map. So now let's move on to what can we do better for distributed infrastructure. And it's good to first start and look at what does a traditional seismic landslide hazard map look like. And this is for the Santa Susana Mountains, north of Simi Valley, and everything in blue is a landslide zone. So basically, anything that is moderately steep is a landslide zone. But that doesn't help us evaluate the potential damage to the infrastructure, because if we think about, again, a pipeline, because our project was focused on pipelines, if this is the pipeline route, and I want to know how the landslide affects the pipeline route, what do I need? I need to know the size of the landslide, and in particular, the exposure length to the pipeline. This is not going to give me that. I need the displacement, and I need the displacement direction, because what matters is the direction of displacement relative to the orientation of the pipeline. So there's a mismatch here between what we're giving out in the landslide hazard world to what is needed for infrastructure assessment. So how do we match the puzzle pieces together? And this is some work that we've submitted to engineering geology, talking about how to translate these grid-based displacements into realistic landslide zones. So we're going to start with those grid cell sliding displacements. We're going to identify landslide zones using that median displacement map I showed you previously, but also something called slope units. And then within the landslide zone, we're going to give you the statistical distribution of our estimate of the displacement, the size, and the direction, because that's ultimately what's needed. So let's dig into this approach. So as I showed you earlier, this is just for a test region. We generate that map of median displacement across the entire logic tree for a ground motion scenario. Then we pick a threshold. 5 centimeters is a common threshold that's used to identify seismic landslide hazards. So we use that threshold to identify landslide zones. But notice those are some big landslide zones. This, you can't quite see that, but that scale is like 200 meters. So these could be a kilometer long. And then we stole something from rainfall-induced landslides with something they call a slope unit, so that trying to identify that slopes that kind of act together. And so we take the landslide zones, the slope units, and we segment those landslide zones based on the slope units. And then within each landslide zone, we define those statistics that I mentioned. So just show you a little bit more about slope units. They represent a half of a catchment basin. It's constrained by ridges and a valley. Generally, they have a similar aspect. Hydrologic conditions, obviously this was originally done for rainfall-induced landslides. And it's relatively easy to compute from a DEM using various packages that are out there. So in this case, again, here's a zoom-in version of those slope units. So you can see this slope area is different from this one. We then overlay our brown blobs of slope zones or landslide zones. And then now you can see each of these are individually colored based on segmenting them out from the individual slope units. So it's these segmented landslide zones that we're going to identify. Okay, so now back to this pipeline risk assessment. What do we need? We need displacement. So we're going to relate that to sliding block displacement. But something I neglected to mention in the beginning is when we've used these sliding block analyses, we often think of them as an index for seismic performance, not like I go out and measure with a tape measure that displacement. So we're going to have to deal with that. What about exposure length? Well, clearly that should be related to the landslide size or width, so we'll deal with that. And then direction of movement is easy, relatively, because we know that soil moves downhill. So what we're going to do is we're going to look at the DEM, and we can identify the direction of down slope, or the aspect of the slope. We're going to define that relative to north. And then no matter what pipeline orientation you have, you just compute the relative angle between the two. But again, the two things we have to resolve is how do we relate sliding block displacement to true landslide movement, and how do we compute pipeline exposure length? So this is where we actually had to talk to the structural engineers who did the fragility models for the pipelines. Okay, so they ran millions finite element models, looking at different displacements, exposure lengths, directions. And they developed these fragility models, so we needed to understand from their framework what mattered. So these were the 6 displacement bins that they developed for their fragility models. These were the 5 exposure lengths from less than 10 meters all the way up to more than 200 meters. So again, that's this width right here. So this is where we had to make some assumptions. First thing is we made an assumption that the exposure length is equal to the landslide width. And then we said, well, let's just assume it's the simplest assumption that landslides are equidimensional. Numbers would change a little bit if you gave it an aspect ratio. But if it's equidimensional, if we can estimate the landslide area, we just take the square root, and we've got the width, and that's going to be our exposure length. And then the directions, those are, again, easy 5-degree intervals. Okay, so let's deal with displacement, exposure length, and direction. So within a segmented landslide zone, so for example, right here, 220 cells, and we're going to aggregate the cumulative distribution functions of displacement to predict the statistical distribution of displacement in that slope unit. But we have to convert sliding block displacement into landslide movement. And I will acknowledge here, I'm going to do a little bit of hand waving, and I think there's a lot of work that can still be done in this area, but this was our best estimate first cut. So first of all, even though we say this huge hillside may all have the same landslide hazard, if you go out after an earthquake, almost never is the entire slope failed, okay? Some parts will have not failed. So we're going to acknowledge that by saying any of the parts of our logic tree that are below, say, 1 centimeter represents no landslide. So then we said, well, from 1 to 5 centimeters in sliding block world is the smallest bin in their fragility curve, which was less than 30 centimeters. We went to the next bin, like 5 to 30, and these thresholds here, I want to note, come from what people have done on regional landslide assessment, but mostly trying to predict yes, no on a landslide, not displacement. But so 5 to 30, we put that in the second bin. So this is the first bin, that's the second bin. After that, it was really hard to justify which displacement went with which. So we took whatever probability we had left, and we exponentially distributed it among the 4 remaining bins. So for this model, or for this landslide zone, you might see this where there's 38% probability of no landslide, and then here's the distribution of the remaining 6 displacement bins. Now what about exposure length? So obviously I've mentioned already, exposure length will be related to landslide area. But it's unlikely that the entire landslide zone is going to fail. Smaller landslide zones are possible, or smaller landslides in the landslide zone are possible. And this is where we went to the field and empirical data and look at empirical distribution for landslide area, but always truncating it at the size of the landslide zone. So here's the landslide, empirical landslide area distribution we use. This was published in 2004 by Malamud et al. And what's shown here is probability density as a function of area. See, it peaks and then it rolls off. And what's really interesting here is they looked at the landslide inventories from the Northridge earthquake, a snowmelt event, and a rainfall event. And all those data, except down here where they're too small to identify, they really tended to fall in along the same distribution, which gives you some confidence that this is somewhat of a unique parameter. And there are different published models we could have used, but this is, at least for this first cut, we used. So we're going to use this empirical distribution for within the landslide zone, but truncating it, because no landslide should be bigger than the landslide zone. Kind of like the virtual rupture concept that Julian was talking about yesterday. The rupture can't go outside of the source area. Landslide should not be bigger than the landslide zone. So if we put that together, we take those exposure lengths, right? Those were the bins that the structural engineers gave us for the fragility models. We related them to landslide area. You can think of it either way. So the exposure length is the square root of the area is the square of the exposure length. And then we went to that empirical distribution, just calculated the area under the curve for the different bins. And you can see This gives about 77% probability of that middle bin. It's showing you that big landslides are not very common as you go down to the tail of this distribution. So this is kind of your baseline distribution for that landslide zone I was showing you that had about a 7,500 square meter size. If we truncate that, it's going to change it a little bit. When we bin it into a histogram, the blue is the baseline without any truncation. The gray is truncated based on the value I just showed you. So these go away, and we just redistribute that probability to the smaller zones. And then direction of movement, again, we can just use DEM tools to look at the slope aspect or the direction it's going to move. But remember, every cell has a different aspect. So we don't know where the landslide is going to happen. So what we do is look at just a histogram of the slope aspect, and that is what we consider the statistical distribution of the landslide movement. So putting this all together, how do we hand this off to the pipeline people? We've got the ground motion scenario. We've got the segment. So given that ground motion scenario, we come up with our segmented landslide zones. And then for each landslide zone, we have a displacement distribution, an exposure length distribution, and a direction distribution that they can then aggregate across to look at the probability of failure at different locations, aggregate among the entire distributed infrastructure to look to risk to the system. Now, when you think about having run this analysis and the computational requirements, we ran the entire state of California, 425,000 square kilometers or so, 4.25 billion cells at 10-meter resolution, and just the data size got massive, and the number of calculations, although each is simple, just a lot. It requires parallelization, high-performance computing, and significant storage, and we were fortunate, as Kyriazis mentioned, to have access to the Design Safe Cyber Infrastructure and our Texas Advanced Computing Center, otherwise known as TAC. So I'm just going to pivot a little bit and talk to you a little bit about Design Safe, not only with respect to how we used it, but how you might use it. And if you think about the research ecosystem in natural hazards engineering, earthquake engineering, we have data that's critical to the work we do. Then we do something to it. We've got data analytics, algorithms, tools we want to run on it. And then those tools and data have to run somewhere. We have some computational resources. And very quickly, we're starting to scale off of our laptops and our desktops. So we need something that pulls all of these things together. Often we call that the missing middle, and that's where the cyber infrastructure comes to play. And that's what we're trying to provide through Design Safe. So our vision for Design Safe is to provide you as researchers the cyber infrastructure that's integral to the research that you do by giving you a platform to share and, more importantly, publish data, enable research workflows and access to high-performance computing, and give you tools that run in the cloud on those resources with access to the additional data. And I can't emphasize this enough, that this is available to the global community of natural hazards researchers. You can join and get an account for free today. You can download data without even getting an account. So if you want to just check out what we've got, go for it. Just a little bit of detail on the components. We've got our data repository, the data depot. We also have a reconnaissance portal if you're interested in reconnaissance data. We've got our cloud-based tools that run on the high-performance computing resources. And then also, of course, we need to explain how to use it all, so user guides and user support. But what I really want to emphasize today is, as researchers trying to make an impact on practice, as practicing engineers who want to use new tools, we should be publishing electronically, not just our data, but our research products. And here are just some examples from the Data Depot in the Publish section. Any of you who know about NEIS, we have the NEIS data in there too. But here, let's take a look at my data, because I got to put my money where my mouth is. So for every paper we submit now, my student needs to publish a data set with scripts, and we cite it in the paper. So these are the LS-DYNA simulations I talked about in the beginning of my talk. So we've got a description, it's documented. Of course, we have a DOI, we tell you how to cite the data. But look at this. We have the motions, we have the finite element models. If you want to build off of those, you want to take them and run them, go for it. We have the compiled output from the simulations. Maybe you're better at statistics than I am. Maybe you want to see what you can do. Why with it? Why run another 50,000 slope models? Pull our data out, go for it. There's so many new AI machine learning models. I'd love to see what you can do. Lastly, if you just want to use the models, right? Yeah, you could go to the paper and put it in a spreadsheet. The ANN, the neural network model, yeah, it's not super complicated. You probably could code that up too, but we've got Python scripts. Download them, use them, quickly you're up and ready to go. And this is the way to make a broader impact. And notice, this isn't experimental data. I'm publishing simulation data. We often don't think of simulations as producing data, but it absolutely does. And also, you might say, I have no idea why or how someone would use my data, that I don't need to do this. Well, I mentioned that example to a colleague, and they said, wow, like about someone who said they didn't think their data could be used, and they said, wow, I wish I had that data. I could train XYZ. So you never know how someone's going to use your data someday. And this leaves a legacy for that to happen, maybe next year, maybe 5 years, maybe 15 years later. So make your research count. Make it reproducible, make it reusable. So I'm going to formally, I want to encourage us all, and encouraging the practicing engineers to challenge the researchers to do this, to publish our data, our products in stable repositories. It doesn't have to be design safe. You may know Zenodo, it's very popular in Europe. Your university may have a Dataverse data repository. As long as it has a DOI, a permanent location, not just a website, it has a DOI, go for it. And again, not just the data, maybe the scripts, maybe the models, maybe the outputs, maybe the visualizations. And then when you publish and use data, cite it in the reference list. Don't put it in the acknowledgments. Don't put it in the abstract. Look, here's an example. Cite it just like a paper. Here's a citation for one of our older data sets. Okay. Now, to go back and summarize, I talked a bit about the evolution of seismic slope performance models, where we've moved from sliding block analysis to stress deformation analysis. If you take one thing away, PGV is one of the best ground motion parameters out there, and in our case was the most efficient intensity measure to predict displacements. The slope parameters KY and T slope and the depth of the sliding mass influence the ultimate displacement. And it was interesting to see how a neural network could more fully capture data trends across all the input variables without needing to come up with a complex functional form. When we then head to regional scale seismic landslide assessments, we need to incorporate the uncertainties, utilize multiple displacement models, and in fact, these comments are applicable to site-specific analysis too. It's just the uncertainties tend to be smaller. And then when we move on to infrastructure risk assessments, we really need to deal with that disciplinary connection. We need to understand how our data and our results are going to be used. So we need to consider those needs, and it will depend on the type of infrastructure. If you're dealing with road cuts or train tracks or bridges versus pipelines, they may be different. And for the work that we did in pipelines subjected to landslides, what mattered was size, ground movement, and direction of movement. And then, of course, I'll end saying encourage you again for the formal electronic publishing of your research products, so we get the full realization of our research investment. And of course, I need to end with a couple of acknowledgments. So my two students who worked on the research that I presented today, Young-Kyu Cho, who is at UNIST in South Korea, and Dr. Olade Ojimo, who's at a pipeline company, Rosen Next in the US. And then for that large CEC project, I was just one part of the geohazards project with John Stewart, Dominique Yasamaki, Paulo Zamaro, Pengfei Wang, and Greg Lavrentidis, and of course our funding agencies and partners. So thank you very much.
Excellent, inspiring. It's the time to get a small gift.